and its bulk deformations of open topological strings.
Okay, so first and foremost, I'm grateful to the organizers for giving me the opportunity to speak here, and to you for choosing this talk to listen to. So I'm going to talk about bulk deformations of open topological string theory. This is based on work with Niels Kalkwyl. Okay, so a genus zero open topological string theory consists of the following amplitudes. So psi's are boundary operators. The UI are certain free moduli. And so you have to imagine a disk with boundary insertions. And you fix 3 points because of SL2R symmetry, and then you integrate over the positions of all the other insertions in between. So actually, this is roughly what it is, because one should also regularize. Here you have an integral over simplex, but actually you should truncate that, and that's actually a crucial point. But anyway, so the space of boundary operators will be denoted by H. Now, the aim is to construct amplitudes deformed by bulk fields. So you see that I've inserted the exponential of bulk integrated descendants phi with moduli t. So we give an explicit construction for those bulk deformed amplitudes, and the procedure essentially splits into 2 main steps. The second is completely general. The first is restricted to affine Landau-Ginzburg models, and we'll see that the aim is achieved via, let's say, close to open topological string field theory, so to speak. Okay, so first of all, let's remind what the underlying structure of those boundary amplitudes is. So this is an infinity structure, so let's remind what that is. So let A be a Z2-graded vector space. So we will denote the tensor coalgebra of A as follows with the usual coproduct. Now, an endomorphism of TA delta defines an infinity structure on A if it satisfies 2 properties. The first is a co-Leibniz rule, so it's a co-derivation. And the second is that it squares to 0, so it's a differential. Now, the squaring to 0, well, I'll say maybe later. So, well, in particular, the first property tells us that the delta is determined by the many-to-one maps, M to 1. Okay, so now we will denote this amplitude as follows: psi A0 Mn, psi A1, psi M. The Mn are so-called higher maps. Now we want to encode the Mn's into a nice structure. So we will define a co-derivation del tilde of Th, whose many-to-one maps are, well, a shift that's not so important of those higher maps Mn. Then the word identities for the BRST operators are equivalent to the statement that delta tilde squares to 0, namely that it is an infinity structure. In particular, it's minimal, meaning that R0 and R1 are equal to 0. So you can see this as follows. You look at the disk with boundary insertions, and when you go to the boundary of the moduli space of the disk with boundary insertions, you find those bubblings of the disk into 2 disks, and the integral over the boundary of moduli space is equal to 0 is exactly this statement here. So the fact that you always bubble into 2 disks corresponds to the fact that you have a square on the delta tilde. So this is ubiquitous everywhere, also for higher genus Riemann surfaces, except that the integral does not vanish. Okay, so now let A be a DG algebra. So it's again also an infinity structure. This would be the off-shell infinity structure. So namely, this is the ingredients of the string field theory that descends to the open topological string theory. So again, DG structure is essentially the same content of a Chern-Simons theory. Of course, you still need a pairing. So you have a differential. The differential, so del 1 corresponds to the differential, the BRST differential, and the 2 is the product of string fields. And with this data and a pairing, you can write down a formal Chern-Simons theory. So now the question is, how do we extract from this simple structure the topological string theory? And there is a theorem, the minimal model theorem, that tells us that up to infinity isomorphism, up to reparametrizations, there is a unique there is a unique morphism and infinity structure on shell, so on the topological string theory, determined by the string field theory. And this corresponds essentially to the tree construction in the string field theory, and the only ingredient needed to specify this is a homotopy G for the BRST differential R1. So everything seems nice and easy. The problem is that the infinity structure is not the only structure that underlies those amplitudes. There is another global supercharge, the conjugate to Q to the BRST differential, and its corresponding word identity tells me that the pairing has to be cyclic with respect to the infinity structure. So this restricts the choice of G. Question, how do we find the right cyclic minimal model? And the resolution, well, so there is an algorithm developed by Karkeville, which builds on results by Kontsevich and Soiberban on non-commutative symplectic geometry. So in particular, we will see later that we will construct the off-shell, say, Kapustin-Lie pairing, and this would, in a sense, this is another side result. This completes the structure of the Landau, well, string field theory for the affine Landau-Ginzburg theory. Okay, so now we look at bulk deformation. So we insert the exponential of bulk integrated descendants, and this deforms the higher products to higher products that depends on the moduli T. And in particular, this deforms the infinity structure to a new infinity structure. This time it's curved. So in particular, the old vacuum will not be the vacuum anymore. This is what introduces curvature tadpoles. So more generally, let's consider the deformation problem of the A infinity structure. So let's consider all possible deformations. And the aim will be to classify all solutions to the Markov-Tan equation. So this is what we do, which are bulk induced. And now let's, well, maybe something familiar is that if we look at perturbative solutions to first order up to reparameterizations, those are classified by, so there are elements in the Cauchy cohomology of the A infinity algebra. And it's the deep theorem by Costello that the Cauchy cohomology of an infinity algebra is equivalent to the universal bulk sector attached to the open sector. And okay, so now we'll talk about Landau-Ginzburg models, affine Landau-Ginzburg models with isolated singularity. So there we have a superpotential W, which is a polynomial, and the boundary, well, we consider one brane D, which is an element, well, it's a 2n matrix with polynomial entries. We will call this algebra A, because it will be our off-shell algebra. And this is a matrix factorization, so it squares to W. Now the TFT data, well, the closed TFT data, you have a commutative Frobenius algebra. The open is a, well, non-commutative associative Frobenius algebra with some sewing relations, pairings, and so on. So here, important thing is the space of bulk fields. This is the Jacobian. And of open fields, this is the cohomology with respect to the BRST differential of H. Okay. So what about off-shell? So the level of the string field theory. Then in affine Landau-Ginzburg models, the underlying space is the space of polyvector fields endowed with the structure of a differential graded Lie algebra, which governs pure bulk deformations. So the differential is the contraction with W, and the bracket is the Schouten-Nihenhuis bracket of polyvector fields. What about the open sector? So there the string field theory is given by A, so matrices polynomial entries, with the DG structure, where the differential is the BRST differential, so the commutative with the matrix factorization, and the product is matrix multiplication. Now the strategy to classify and compute all the solutions to the deformation problem is as follows. We consider the DG Lie algebra that governs the deformation problem of the pure bulk, and we map this concretely to the open sector. So the right notion of, well, the right map that we have to construct is an L-infinity morphism. So Mark-Cartan equations are covariant under L-infinity morphisms. So step one will take place all in the string field theory side. So we will map the closed string field theory to the open string field theory. And step two, we go on shell. Okay, so then given a pure bulk deformation gamma, the solution to our deformation problem will be given as follows. Del tilde is a sum of S and 1, the higher maps of the L-infinity morphism applied to gamma wedge n. So it's just the induced deformation by the L-infinity morphism S. This is what defines induced bulk deformation. Okay, so let's start with step one. So we want to map the closed string field theory to the open string field theory, and this is achieved in three main steps. The first one, so we will work our way backwards. We start with, on the right-hand side, with the open string field theory, and we try to make it the structure as associative as possible. We can't make it completely associative, but we can map it to a curved associative algebra. So that's what the 0 stands for on the left-hand side. Add T is the an infinity quasi-isomorphism induced by the a infinity curved isomorphism T. And T has two higher maps. One is the 0 to 1 map. This is just a matrix factorization and the identity. Now this T01 is what is responsible for the presence of the matrix factorizations D in the Kapustin-Lie pairing. Okay, and this curved algebra, the product is the same product as before, and the tuple, the curvature, is the minus the potential W. The second, the second map is the code trace map. So now we are there with our curved associative algebra, and we can go backwards to co-derivations of TR, where R is just the polynomial ring. So we map this curved associative algebra to a commutative curved associative algebra via a graded version of the code trace map, and this is a generalization of Morita equivalence. Particularly, this code trace map induces an L-infinity quasi-isomorphism again, and you can show that it's again a so it induces a quasi-isomorphism again, and you can show that even when you have curvature, this is still a quasi-isomorphism. So now the third, maybe more conceptual step is a curved version of deformation quantization. So now we've reduced the whole problem to mapping the pure bulk sector T-poly to co-derivations of this commutative algebra. So maybe you will see immediately that what happens when W is equal to 0. Well, when W is equal to 0, the solution K is Koncevich's L-infinity quasi-isomorphism. So in particular, in what do you do in deformation quantization? You consider a classical system, and the only structure you're interested in is the algebra of observables, which is just, so you have a smooth manifold, you look at the algebra of observables, and now you want to understand what the algebra of quantum observables is. So you deform the pointwise commutative product to a non-commutative product anymore, but it must be with hindsight still associative. So this sets up a deformation problem. This is what deformation quantization is. So we postpone the problem of representing the algebra on some Hilbert space, and the solution is to find a little DG algebra, that governs this whole deformation problem. And this is the Lie algebra of polyvector fields. It's actually just a Lie algebra. It's formal, and the solutions to the Mark-Cartan equations here are simply Poisson structures. So for every Poisson structure, you have a commutative, you have a quantum theory. In this case, we will have the bulk ring. Okay, so the above deformation quantization when W is equal to 0, it's a very pleasant surprise that when W is not equal to 0, Koncevich's morphism is still an L-infinity quasi-isomorphism. Okay, so this concludes the string field theory part. And maybe here it's a good point to sketch how to construct the Hofstede-Kapustin-Lie pairing. So in the non-commutative geometry language, the pairing is promoted to a homologically symplectic differential form on BA, which is the tensor algebra of the dual of A. And Q, so the infinity structure is encoded in its dual Q, which is a canonical vector field in this language. And now you can map this with some canonical construction to C0. You map it now to the cyclic to two incarnations of the cyclic complex, which are related by a DG version of a map constructed by Cassel for associative algebras. Then you can push forward this with a tadpole with our translation map from the DG structure to the curved associative one. Then you have the supertrace. Then you use Hochschild-Constant-Rosenberg, which is the first-order version of Koncevic, and you arrive here. So notice that you have a non-vanishing D, and then the last map is a map of complexes from here to here, and this is not anymore the residue pairing. It's a cyclic residue pairing, and you can find it via homological perturbation. Okay, now in the last few minutes, I will talk about the latter part, so how to map off-shell to on-shell. So, and this is completely general for any topological string theory. So the key observation is that the infinity structure on-shell is a deformation retract of the infinity structure off-shell. So it's important to stress that the minimal model theorem is something that happens at the level of H and A, and here instead we have TH, TA, and instead of the little BRST differential, we have the whole infinity structures. So what is a deformation retract? Well, it consists of the following data. You have an inclusion map, which in this case is the minimal model morphism F. And then you still have to find a projection map, which will be a homotopy inverse to F, and the homotopy U acting off-shell. So we construct that, and this is a similar result, but it was about deformation, homotopy retraction data for coalgebras was studied by Guggenheim, Blambes, Tashev in late 80s, early 90s. They had a different kind of homotopy. This is the correct one, and it's completely explicit, and it's compatible with this tree construction for minimal model morphism. The important thing is that it's in so-called standard form, and this makes sure that it preserves the coalgebra structure. So then the only thing we need to do is to map, using this data, co-derivations of TA to co-derivations of TH. This is again given by an L-infinity morphism. It's not a quasi-isomorphism as the one before. In particular, not all bulk-induced deformations should be non-trivial given a single brain. And the explicit map is as follows. And then we find that del tilde, the deformation, is given by the simple formula. So this is the L-infinity reformulation of the homological perturbation lemma, and this finishes the whole program. And the nice thing is that with this Hofstede-Kapustin-Lie pairing, that is, well, there are still a few things that have to be made rigorous. You can speed up the computation of the minimal model morphism, so all of this is very nice, concrete, and applicable in a fast way. Okay, that's it. Okay.
How does it compare to this calculation of, I mean, the bulk
so you're asking how to go to the large volume limit. Yeah, so right, but the thing is that so all of this is the non-graded case. So for the one would still have to do the graded case, I guess, no? So this is also possible, and but we haven't analyzed that yet. So the whole point is that one should replace the Jacobian by a corresponding to Rive algebra, which is the semi-direct product of the group, which gives you the gradient with the invariance in the Jacobian. And then you can do probably the whole procedure, and then at that point one might check out.
Another question I had, is there anything that you can say about the analysis?
Not yet. So this would be the first example that we'll have to. So at this point it's yeah.
Well, according to Castellan, it should be encoded in this.
Ah, sure. I mean, how to go to higher general? I mean, I have some.
Let's do the analysis.
Yeah. But well, I have some ideas of maybe how to go to higher general.